Somewhere in Vietnam, there are closed farming systems running around the clock, sorting, harvesting, and scaling up production of a small creature that once sent rice farmers into a panic. What's strange isn't that they're farming it. What's strange is how deliberately they're doing it at a scale that suggests this isn't an experiment. It's already a system. Inside a facility in Vietnam, rows of concrete tanks sit in structured lines. Water moves through each one in a controlled cycle. Workers move between them, checking, sorting, collecting. It looks like any mid-scale aquaculture operation. There's a staging area for juveniles, a separate zone for harvest-sized stock, a processing table where animals are washed, graded, and prepared for distribution. The output is consistent. The system is deliberate. Nothing about it looks unusual until you know what's living inside those tanks. The species being raised here isn't tilapia. It isn't shrimp, catfish, or any of the conventional animals you'd expect to find in a Vietnamese farming operation. It belongs to the genus Pomacea. Specifically, Pomacea canaliculata, a name that appears on a list most agricultural scientists would recognize immediately. The IUCN's Global Invasive Species Database ranks it among the 100 worst invasive species on the planet. Not the worst 100 in Southeast Asia. Not the worst in aquatic environments. The worst 100 globally, across all categories of invasive life. That's what's in those tanks. The workers handling them aren't wearing hazmat gear. There's no emergency signage. The operation runs on a regular schedule, like any other farm producing protein for a regional supply chain. From the outside, it looks like a solved problem, a species brought under management, integrated into a production system, generating output. But the classification doesn't disappear just because the setting changed. Pomacea canaliculata earned its place on that list for specific biological reasons. It arrived in parts of Asia during the 1980s, introduced deliberately in some cases as a potential food source. What followed wasn't a controlled expansion. It was a breakdown, the kind that happens when a highly reproductive species moves into an environment without the boundaries needed to contain it. What you're looking at in these Vietnamese facilities is a different attempt at the same idea. The species hasn't changed. The biology is identical. What's different is the structure around it. And that structure is doing something the 1980s introduction never had. It's keeping the animal inside a defined boundary, separated from the open water systems, the rice paddies, and the irrigation channels that made the original spread possible. Whether that boundary holds, and what it actually takes to maintain it, is the question the rest of this story is built around. To understand why this species becomes dangerous outside a controlled system, you have to start not with the snail itself, but with the plant it feeds on. According to research from the International Rice Research Institute, IRRI, both direct-seeded and transplanted rice go through a critical vulnerability window in the first 30 days after planting. During this period, the stems are soft, the root systems are still establishing, and the plant has almost no structural defense against grazing pressure. If something eats the stem at this stage, the plant doesn't recover. It dies. A farmer doesn't lose one stalk, they lose the entire hill, and depending on the timing, the entire plot may need to be replanted from scratch. Once rice reaches 30 to 40 days old, the picture changes. The stem thickens, the tissue becomes harder and less palatable, and the plant develops enough structural resilience to survive moderate feeding pressure. The same snail that could wipe out a seedling at day 10 will cause far less damage to a plant at day 35. This is the core of the problem. Not that the snail is aggressive by nature, but that it exists in the same flooded water environment as young rice, at exactly the point when young rice is most exposed. Think of a newly built wall that hasn't fully set. A light push at the wrong moment causes a collapse that a much harder push couldn't cause a week later. The vulnerability isn't permanent, but the window is real. And in a flooded paddy field, there's nothing physically separating the snail from the seedling during that window. That timing problem becomes a regional problem when you consider how Southeast Asia's agricultural systems are built. This is a part of the world where wetland rice cultivation covers tens of millions of hectares. The fields are flooded by design. Water is the medium, everything moves through irrigation channels, seasonal rains, shared waterways connecting one farm to the next. A species that thrives in standing water and feeds on aquatic vegetation doesn't need to travel far to find the next field. The infrastructure that makes rice production possible also makes containment extremely difficult once a population is established outside any kind of boundary. Vietnam sits at the center of this dynamic. Its lowland rice regions, particularly in the south, are laced with water systems that have been built and expanded over generations to support continuous cultivation. It's a landscape designed around water movement, which is exactly the kind of landscape where a highly mobile aquatic species can spread without much resistance. And here's where the history of this particular snail becomes more complicated than it first appears. Pomacea canaliculata didn't arrive in Asia as an accidental stowaway. In a number of countries across the region, it was introduced deliberately during the 1980s. The reasoning at the time had a logic to it. The snail was protein-dense, it reproduced readily, it could be raised in water-based environments already common in farming communities. The idea was to give rural households an accessible source of food and income. What the introductions didn't account for was what happens when a species with those exact biological traits, fast reproduction, water-adapted mobility, appetite for soft vegetation, escapes into the same flooded systems where rice is grown. Once it moved beyond the initial holding areas, it found an environment it was effectively built for. The controls that were supposed to keep it in place weren't strong enough, and the populations expanded into the rice-growing landscape faster than anyone had anticipated. So the same qualities that made it seem like a promising food source in the 1980s were the qualities that made it a pest problem by the time those introductions had run their course. The animal didn't change between those two conclusions. The difference was entirely about where it was placed and whether the system around it was capable of keeping it there. That question, what kind of system is actually capable of containing it, is exactly what separates what happened in the 1980s from what Vietnam is attempting now. So the question now is not whether this species is dangerous. It clearly is, under the wrong conditions. The real question is, what does it actually take to keep it contained? The answer comes down to three boundaries. Not one, not two, all three have to hold at the same time. Remove any single one, and the model breaks down in a way that's difficult to reverse. The first boundary is biological. Pomacea canaliculata reproduces at a rate that makes loose management genuinely risky. Eggs can hatch in as few as 10 to 15 days under warm conditions. That means a farming operation that loses track of its egg clusters for even a short period isn't just dealing with a nuisance, it's dealing with a population event. In a controlled system, this means egg collection has to be consistent, juvenile populations have to be monitored, and the reproductive cycle has to be actively managed rather than passively observed. The biology doesn't pause because someone isn't watching. If the first boundary fails, everything downstream becomes harder to defend. The second boundary is physical. Concrete tanks and enclosed systems matter, but the physical barrier isn't just about the walls of a tank. It's about every connection point between the farming system and the wider water environment. Vietnam's lowland agriculture is built around an extensive network of irrigation channels, drainage ditches, and seasonal floodwater. A single overflow event during heavy rain, a gap in drainage management, or a poorly sealed outlet can introduce a population into exactly the kind of flooded, vegetation-rich environment where this species thrives. The physical boundary isn't a one-time construction problem, it's an ongoing operational discipline. The difference between a controlled farm and an uncontrolled release is often a matter of infrastructure that holds under pressure, not just under normal conditions. The third boundary is economic. This one is less obvious but arguably the most important for sustaining the first two. Biological monitoring costs time. Physical containment costs maintenance. Neither of those gets done consistently if there's no financial reason to do them. When a species has no market value, every resource spent on controlling it is a pure cost. It drains from the operation without returning anything. But when the same species generates revenue, the logic shifts. Farmers who are collecting snails for sale have an ongoing incentive to monitor populations carefully, because a mismanaged tank doesn't just create a biological risk, it creates a loss. The economic boundary essentially turns the control effort into something that sustains itself. This is why the scale of rice production in the region makes the third boundary impossible to overlook. According to U.S. DAFA's projections, the Mekong Delta alone, Vietnam's most productive agricultural zone, is expected to produce approximately 51 million metric tons of rice across 84 million hectares in the 2024-2025 crop year. That's not a background detail. That's the stakes. Farming an invasive species at scale in a country where rice production of that magnitude depends on water system integrity is not a casual decision. It only makes sense if the system maintaining containment is robust enough to hold under real operating conditions, not just ideal ones. And that's where Vietnam's approach becomes genuinely interesting, because what's being tested here isn't just a farming technique. It's a hypothesis that a biological risk can be made manageable through a production model rather than through the kind of direct suppression campaigns that have repeatedly failed to produce lasting results elsewhere in the region. The tanks aren't just growing snails. They're testing whether all three boundaries, biological, physical, economic, can be maintained simultaneously at a scale that actually matters. Whether that hypothesis holds depends on what happens when one of those boundaries is stressed. Remove the market and farmers stop managing populations carefully. Weaken the physical infrastructure and populations enter the drainage system. Let biological monitoring slip and reproduction outpaces harvest. Each failure mode points back to the same conclusion. The system works only as a complete set, three boundaries or none. There's a straightforward way to think about why containment systems fail over time, and it has nothing to do with biology or infrastructure. It has to do with incentives. When a species has no commercial value, every action taken to control it is a cost: labor, time, chemicals, monitoring. The people doing that work have no financial stake in how well it's done. There's no return on precision. A farmer who spends 3 hours meticulously checking drainage barriers gets the same outcome, in economic terms, as one who doesn't bother. That's not negligence. That's just how uncompensated effort works over time. Without a reason to maintain control continuously, control degrades. Now consider what changes when the same species has a buyer. Suddenly, the population inside the system isn't a liability to be managed. It's inventory. A farmer who monitors egg clusters carefully isn't just preventing a biosecurity risk. They're protecting the yield that generates income. A worker who maintains the drainage barriers isn't performing a cost. They're protecting something worth selling. The economic boundary doesn't just add a revenue stream. It restructures the logic of every decision made inside the operation. This is why the question of market access matters as much as the question of tank design. And it connects to a much larger pressure that had been building in the aquaculture and livestock industries for years before any of this became relevant to golden apple snail farming. FAO data shows that fish meal prices, one of the most widely used protein sources in commercial feed, sat at roughly $500 to $700 per metric ton between 2000 and 2005. By May 2008, that price had climbed to approximately $1,210 per metric ton, nearly double in just a few years. At the same time, in 2007, the aquaculture feed industry was consuming around 6.8 million metric tons of soybean meal annually, accounting for approximately 25.1% of total industrial aquaculture feed by weight. The industry was running on expensive inputs and searching for alternatives that could be produced locally at lower cost, without depending on global commodity markets. A species that reproduces readily, can be raised in controlled conditions, and produces biomass at scale starts to look different against that backdrop. Not as a pest to eliminate, but as a potential local protein source for feed systems that were already under cost pressure. The snail itself didn't change. What changed was the context around it, a context that made a market for it not just possible, but structurally useful. Think of it this way: a species without a market is biological waste, something to be cleared, controlled, and discarded at ongoing expense. Once a processing and purchasing chain exists, the same material becomes a raw input. The act of harvesting it becomes revenue-generating rather than cost-generating. And critically, the incentive structure that holds the entire containment system together, the biological monitoring, the physical barriers, the operational discipline now has a reason to sustain itself. But that logic cuts both ways, and it's worth being clear about the risk on the other side. A market that grows faster than the containment infrastructure can keep pace with is not a safeguard. It's a pressure. If demand outpaces the capacity to maintain boundaries, if producers expand operations before the physical and biological controls are proportionally strengthened, the third boundary that was supposed to hold the system together becomes the reason the system fails. The economic incentive accelerates production. The containment discipline doesn't keep up, and the result is not a farming operation that got too successful. It's a population event. So the market isn't a solution by itself. It's a tool that works only when it's running in parallel with the other two boundaries, not running ahead of them. Here's something worth sitting with for a moment. The idea of using golden apple snails as a protein source isn't new. It's actually the reason the species ended up in Asia in the first place. Starting in the 1980s, Pomacea canaliculata was introduced to several parts of Asia, including the Philippines, deliberately. The reasoning seemed sound at the time. Here was a species that reproduced quickly, could be raised in water-based systems already common in rural communities, and offered a local, accessible source of animal protein for farming households. It was brought in as a resource, not as a threat. What happened next is well documented. Once populations escaped from initial holding areas and moved into open water systems connected to rice-growing land, the same biological traits that made the snail seem useful became the engine of a pest outbreak. It wasn't that the idea was wrong. It was that the idea was running in an environment without the structure to contain it. The snail that destroyed thousands of hectares of rice fields in the Philippines was the same species, with the same biology, as the one that had been introduced years earlier as a food animal. The goal hadn't changed. The outcome had, because the system around it had failed to hold. This loop is worth understanding clearly, because what Vietnam is doing now is not a new idea. It is the same idea, attempted with a different architecture, and the scientific case for why that architecture might now produce a different result has been building steadily. A 2018 study examined the use of golden apple snail meal as a protein source in feed for rabbitfish, testing whether the snail's nutritional profile could support growth in a commercially relevant aquaculture species. The results pointed toward a viable application. Then in 2024, a broader compositional review found that golden apple snail meat, measured on a dry matter basis, contains approximately 67% protein, depending on preparation and processing method. The shell, often treated as waste, contains around 38% calcium, a figure that has its own implications for feed formulation in livestock and poultry systems, where calcium supplementation is a recurring cost. These aren't numbers from a marginal or speculative source. They describe a biomass with a protein density that sits comfortably alongside conventional feed ingredients produced by a species that, under the right conditions, generates that biomass at high volume with relatively low input costs. The contrast between the 1980s introductions and what's being attempted now comes down to a single structural difference. In the earlier cases, the snail was placed into an open system, one connected to the same waterways, floodplains, and rice paddies that made up the agricultural landscape. There was no effective separation between where the snail was supposed to be and where it wasn't supposed to go. The biology did what biology does when it finds favorable conditions and no physical limits. What's being tested in Vietnam's closed farming systems is whether that same biology can be made to work in the opposite direction, not spreading outward through an uncontrolled landscape, but contained, cycled, and harvested within a defined production boundary. Same species, same reproduction rate, same protein content, different container. The original idea wasn't dangerous because it aimed to use the snail. It was dangerous because it had no reliable way to keep the snail in place. An idea without a containment system isn't a strategy, it's a release. The question now is whether the system Vietnam is running is tight enough to be something fundamentally different from what came before. So let's come back to the question this whole video started with. Why would Vietnam, a country whose agricultural identity is built on rice, choose to farm a species that once posed a direct threat to that rice? The answer, when you lay it out clearly, isn't about optimism or risk tolerance. It's about structure. Outside a controlled system, this species is a biological risk. It occupies flooded environments, it reproduces quickly, and it feeds on plant tissue at exactly the stage when rice is least able to defend itself. Left uncontained in the landscape that Vietnam's rice farming depends on, it creates the kind of problem that multiple countries across the region have spent decades and significant resources trying to manage with limited lasting success. Inside a closed production system, the same animal becomes a biomass source. The reproduction rate that makes it dangerous in open fields is the same trait that makes it productive in a contained environment. The biology doesn't change. What changes is whether that biology has an exit, add a functioning market, buyers, processing chains, consistent demand, and the incentive to maintain the containment system becomes self-reinforcing. The economic boundary isn't just a revenue stream. It's the reason biological and physical controls stay in place over time, rather than gradually degrading when no one is watching. That combination is what makes this story worth attention. The Mekong Delta, which accounts for approximately 55% of Vietnam's total rice output and around 90% of the country's rice exports, is not a landscape where agricultural risk management is a low-stakes exercise. In 2024, Vietnam was recognized as the world's third largest rice exporter by export value. A country operating at that scale, in a region where this species has already demonstrated what it does when boundaries fail, is not making a casual bet by introducing closed-system farming of a known invasive. It is making a calculated one, and the calculation rests entirely on whether the three boundaries hold. That's the real lesson here, and it goes beyond golden apple snails. This is not a case study in turning pests into food. It's not an argument for farming invasive species as a general strategy. There are invasive species where no production model would justify the risk, and contexts where closed systems would never be tight enough. The conditions matter. They always do. What Vietnam's approach actually demonstrates is a specific logic. A biological risk only becomes a resource when three things are true simultaneously. The organism is contained at the reproductive level. It is physically separated from the environments where it causes harm. And there is an economic reason for the people managing it to maintain that containment every day, not just on the day the system was designed. Remove any one of those conditions, and the model doesn't produce a smaller version of success. It produces a version of the 1980s introductions, the same animal, the same intent, and the same outcome that followed when the structure around it wasn't sufficient. The question for agriculture going forward may not always be how to eliminate the problems that have moved into the landscape. Sometimes it may be how to design the conditions under which those problems can be kept in a place where they can no longer become one.